Streaking through space, light is the fastest thing in the universe.
It could circle the Earth 7 times in 1 second.
Exploring the mind-bending world of physics, we dive into a fascinating topic: how light travels faster than the speed of light. At first glance, this notion may sound impossible, given that light itself is often considered the universal speed limit. However, recent scientific discoveries have unveiled intriguing phenomena that challenge our understanding of the fundamental rules governing the behavior of light. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space and beyond, consider subscribing. Light moves at a constant speed of 299,792,458 meters per second, according to the theory of relativity. Remarkably, this speed remains unchanged. Even if two individuals are traveling through space at different velocities, one at 1% of the speed of light and the other at 50%. If they both observe the same stream of photons, they will perceive them moving at the same pace. Rather than allowing any variation, time and distance appear to warp when attempting to observe light at a speed other than the speed of light itself. However, it's essential to note that this assertion only applies to light traveling in a vacuum. We've long recognized that when matter is involved, light becomes impeded and moves more slowly. For instance, light in air travels at 299,705,000 m/s, which is 87,458 m/s slower than light in a vacuum. In water, light travels at approximately 225 million m/s, while through glass, it tops out at around 200 million m/s. The underlying reasons for this phenomenon are intriguing, but generally comprehensible within the framework of physics. When light traverses a material, its electromagnetic fields cause the electrons within that material to start moving, akin to ships bobbing on water. However, these moving electrons generate their electric and magnetic fields, creating a second light wave that overlaps with the original light wave. This second wave oscillates at a slightly different rate depending on the material. When these two waves meet, they interact, sometimes constructively reinforcing each other and sometimes interfering destructively. As a result of these interactions, a new wave emerges, which travels at a different speed than the original light, and notably at a slower pace than the speed of light. Eventually, this propagating wave can reach the edge of the obstructing material, where the interference ceases, leaving only the original light to continue along its initial path at its original speed, as though nothing unusual had occurred. Over the years, researchers delved deeply into this concept, yielding captivating findings and experiments. In 1999, Harvard scientist Lin Hao achieved a remarkable feat. She drastically slowed down light, akin to a speed of merely 61 kilometers per hour. This feat was accomplished by directing light through an ensemble of extremely frigid sodium atoms, almost as cold as physically possible, just a hair above absolute zero. 2 years later, Hao momentarily halted the light, later reinvigorating the atoms, allowing the light to resume its course. This may seem astonishing, but an even more peculiar event occurred in 2000, when scientists in New Jersey sent a light pulse through a cluster of atoms. Upon examination, it appeared as if the pulse emerged before it had even entered. This might pose a perplexing conundrum. How could one exit a place before entering it? However, there exists a straightforward explanation. While the pulse seemed exceptionally swift, the actual light itself wasn't. It was akin to an optical illusion rather than a substantial contradiction to Einstein's theories on motion. Light, a fascinating topic indeed. It comprises minuscule bundles of waves, each with its unique wiggling pattern. The rate at which these wiggles travel within the bundle is referred to as phase speed. On the other hand, the pace at which the entire bundle advances is termed group speed. Additionally, there's a concept called wavefront speed, concerning the initial photon's velocity in a group. Picture a stadium wave where the wave seems swift, but the crowd isn't really moving, akin to the group speed or wavefront speed. Now picture trying to make this crowd walk while they keep doing the wave. Even if their waving hands make it look like the wave is rushing forward, it would disappear when it gets to the front. It means that the information can't go faster than the crowd is walking, no matter how fast the wave's peaks seem to be moving. Einstein's idea about how things move never said that phase speed can't be faster than light. It just said that you can't send a message faster than light. So, even if you tried to send a message with a crowd doing a wave, it wouldn't really get there any quicker until the first person reaches the destination. But this difference between the waves inside light and the speed of light itself gets really interesting in our next experiment. This is where things start to get super mind-boggling, way weirder than you might have thought until now. Let's revisit the double slit experiment, which delves into light's dual nature as both a wave and a particle. In 2023, scientists at Imperial College introduced a unique twist. Instead of shifting the slit's position, they manipulated their timing. They utilized a transparent material, indium tin oxide, known for its reflective properties under specific conditions, commonly found in smartphone screens. By swiftly transitioning this material from transparent to reflective and back, they created a minuscule time interval, just a few femtoseconds, during which the laser was reflected, termed a time slit. When they examined the laser's behavior after reflection, they noted a subtle shift in its frequency, but nothing remarkably unusual. The intriguing revelation emerged when they directed 2 laser pulses consecutively through these time slits, leaving all other elements in the setup unchanged, except for the timing of the laser's passage. Remarkably, when they rapidly sent 2 lasers through, an interference pattern emerged. It differed from the typical 3D space double slit experiment, affecting the laser's frequency rather than its spatial pattern. Some colors or frequencies of light dimmed, akin to the fading brightness in the regular double slit experiment. Let's view it through a temporal lens. Imagine representing the time slit experiment in a 4D graph, where space aligns with the x-axis and time with the y-axis. The photon's journey starts from the left emitter, encounters the time slit, reflects, and reaches the receiver. This can be visualized as a continuous line. Later, a subsequent photon follows a similar path, but arrives slightly later, depicted higher on the time graph, signifying a more distant future point. If light behaved as usual and traveled at its normal speed, this would be the end of the story. But light is doing something unusual. It's interfering with itself. This suggests it must be taking a path that goes through not only one slit, but also the other slit. This is the only way that light would create the pattern we see. And just like in the double slit experiment, it's likely happening on the other side of the slits as well. Now, why is it the frequency of light that's changing here and not how bright it is? To understand that, think about what would happen if light came in at a different angle, as we're seeing here. Photons, which are tiny particles of light. Normally, when light waves arrive, they follow a certain pattern, with peaks and valleys like waves in the ocean. However, if you change the angle at which these waves arrive, something interesting happens. The peaks of the waves arrive more frequently, which changes the color of the light we see. Low-frequency light appears red, while higher-frequency light appears blue. What's puzzling is how these waves behave in terms of time. Some parts of their journey seem slower than the speed of light, while other parts appear faster, almost as if they're going backward in time. This strange behavior was observed in an experiment conducted by researchers at Imperial College in London. The implications of this discovery are intriguing. Light typically takes the quickest path to its destination, trying to be as fast as possible. However, it seems that light explores different paths, including ones through time, like it's testing options to find the best route. These feelers of light interfere not only with photons traveling at the same time, but also with those slightly ahead or behind in time. To clarify, we don't actually see photons traveling in these unusual ways, like coming from the future or moving slower than light, unless there are specific conditions involved. Yet for interference patterns to occur, light must be exploring these alternative routes through time, in some manner. It's as if light is testing different directions before settling on the best path to its destination, making all other possibilities vanish. There might be more to this phenomenon than we currently understand. For now, we can only conclude that light doesn't always follow the rules we thought it did.